My name is Glenn Diskin, and I'm the principal investigator for the instrument called the Diode Laser Hygrometer, which we often refer to as DLH. It's flown on a variety of aircraft since the mid-1990s, making water vapor measurements from the Earth's surface up to the stratosphere, from the equator to the poles. And the objectives we have for the ASHRAEX campaign are to measure water vapor concentration at very high accuracy and precision in order to help understand the processes by which water vapor is transported from the troposphere to the stratosphere, and also understand its role in cloud formation at the very high altitudes at which the Global Hawk will be flying. So the Diode Laser Hygrometer, as the name suggests, uses diode lasers, which are found in many aspects of people's lives. These particular lasers are similar to ones used in the telecommunications industry, but they're built specifically for us in order to tune to portions of the electromagnetic spectrum where water vapor absorbs. And we use that absorption of the light by the water vapor in order to make the measurement of how much water vapor is there. And in this instrument, we do this by sending a beam of light from the instrument out to a reflector which is mounted under the wing of the aircraft, and that light hits a reflector which is very similar to the material used in road signs, and so it sends the light back not as a mirror but as a retroreflector back into the instrument, where we can collect enough of that return light to make a measurement of how much of it was absorbed by the water vapor molecules in the atmosphere. Take a look where the optics of the instrument are. This is where the light gets processed, gets sent out to the reflector and back. So this is just a cover that we keep on when it's on the ground. This is a window that's specially coated not to reflect the light at the wavelength that we're using. All the optics are inside this box. So the beam exits this window, comes over to this panel here, and this is the material that's very similar to what you find in road signs. So the light that hits it preferentially wants to travel back in the same direction and go back into the instrument, where we've got a lens that collects the light and focuses it onto a detector where we can analyze it. So that's, in terms of the optics, very simple compared to some optical instruments. It's self-aligning because of the retroreflector material. So it allows us to make very good measurements without having to have very precise control over the pointing. As long as we can hit the target, which we can easily do in flight, then we get signal back and we can make the measurement. So the other part of the instrument is the computer, the specialized computer, and other electronics that are in this housing here. And this computer is designed to supply all the information to drive the laser, to collect data from the detectors, to collect data from other sensors that are inside, both inside here and inside the black housing on the other side, which houses the optics and sends the light out and collects it back. So this is the fiber optic cable which we use to transmit the light from this chassis out to the optical transceiver housing that's on the other side of the aircraft. The signals from the detectors that are inside come back on these black cables here, and other signals go back and forth on these larger cables. So each molecule has its own electromagnetic fingerprint. Water vapor has its own fingerprint, and we use that information, detailed knowledge of water vapor's absorption characteristics, and we take advantage of that by moving the laser wavelength back and forth across one of the specific fingers in that forest of lines that water vapor has, and that allows us to determine the concentration of water in the atmosphere.